Okay, we'll start the class. Okay, so we'll start our class. So now I'm starting from the I think week five question related the doubts about the settling chambers. So here you can see four different types of okay, four different types of settling chambers. Discrete settling is this one, flocculent settling, hindered settling, compression settling. These all four types of settling, we were comparing the velocity. So here you will see the discrete settling as you seen in the figure. In discrete settling, each particle settles independently of others. So you will see here the particles settle individually. So what happens here? The weight of the particles. Okay, so the weight of the particles will be, see, the smaller size means its weight is higher, smaller. So the velocity also will be smaller. This also depends. You see here, the velocity of settling is determined primarily by the particle size, shape, and density, as well as fluids viscosity and density. But when we see the size when compared to other settlings, the particle size, when you consider the whole system, it is small. So related to the fluid character, so here the settling velocity is comparatively lesser. So in flocculent settling, we you see here the flocculent settling, the particles will attach each other and making a like see like a colony, and the weight of this will be increasing, and it can fall little bit higher speed compared to the discrete settling. You see here, in flocculent settling involves the aggregation of particles into a larger cluster or flocks. These flocks settle more quickly than individual particles due to their increased size and mass. So the settling velocity of flocculent particle is higher than the individual particle, but may also vary depending on the flock size and strength of flocculation. So you see here, when we consider the entire system, you see this is a settling chamber. You see this is like two particles are flow like combined together. So here you see one, so here you again see two, here one and three, so three, two, so like that. You see numerous, like you can see different numbers of particles are attached together, and then they are moving. So here you can't predict, or you can't say that uniform velocity for all the different flocks. It depends on the size of individual and how much it is flocked and formed a structure like this. So it's all depend on the like it's the type of combination, and if it's an individual, then the velocity is smaller. So at different positions, the velocity is different for each group. So it is not a uniform velocity throughout the chamber. Okay, then this is the hindered settling. So here hindered settling means, you have to understand here, in hindered settling, particles are numerous. So it is very high, particles are very high, and their settling is affected by the presence of other particles. So the settling velocity of a particle decreases as the concentration of particle increasing. The system typically shows a decreased effective settling compared to the discrete settling due to the particle interaction and crowding effect. So that's why here, compared to the, see, when we compare discrete settling and flocculent settling, see the hindered settling means the number of particles are very high. So this will make a turbulent effect, and it doesn't have, it can't properly move. See, it cannot have the proper path to move. It will collide each other, and it will make a form, make flocks also, but still the effectiveness of coming down is very less because of the collision and all. So that is the hindered settling. So, in compression settling, you see the compression settling occurs when particles are densely packed and causing the sediment bed to compress under its own weight. So, the settling velocity at this stage is influenced by the compressive forces and the formation of cake like structure at the bottom. So, this type of settling leads to a decrease in the sedimentation rate at the bed become more compact. Okay, so here you see in the compression settling, the number of the particles are also very high, and the compression force is there, and that will cause here, you see the it become the formation of a cake like structure at the bottom. So here you see the cake like structure formation, and it will hinder the movement of other particle which is above, and it cannot settle. So this is the difference between the four type of settling that uh, we have discussed on the previous to previous class. So in this, flocculent settling has the comparatively higher uh, settling speed compared to other settling chambers. Also, you have to remember one thing, that at different regions, the for the flocculent settling, the velocity is not uniform. Got it? I hope it's clear now, or else you can raise the question. Anything? Okay. Okay. So now we'll. This question, have you understood this question? Like previous class, we have solved this question. There is one thing. Um, there is one. The unit confusion has came. Go- Okay, then this question we'll take the last, but this, just remember that a unit what we have got for the we can't consider like meter cube per day. We can't take it since the sludge we are considering as a solid. So we are taking as kg per day. So okay, I will again we can just solve fastly, and I will explain. So okay. Okay, now we'll go for the anaerobic wastewater. So now you see, we are going. Okay, so just 1 minute. Okay, so here we are going to take we discuss on anaerobic wastewater. So here, what is anaerobic wastewater treatment? So previous week, what we were discussing is the in mostly in the aerobic condition. So here now we are going for the anaerobic, because we are providing air also, so that we are providing the oxygen in the air in the previous week, throughout the all the examples. Now how we differ from that aerobic condition to anaerobic wastewater treatment. So here see, anaerobic wastewater treatment is a biological process that breaks down water without dissolved oxygen. So that is the major difference. Here we are not considering the oxygen intake. So the main three types of anaerobic reactors. You see here, upflow anaerobic sludge blanket reactor, anaerobic filter reactor, then anaerobic baffled reactor. Okay, so these are the three types of reactors. So now we see what is the difference between this three reactor, and then we'll go for the questions for this week. Okay. So now mainly, what is this anaerobic digestion process? Here you see, in anaerobic digestion means its microbial presence is there, but all the process take place in the absence of oxygen. Okay. So, main type of microorganism that is used in this process are hydrolytic bacteria, acidogenic bacteria, acetogenic bacteria, and methanogens. So then, how this happening? How this organic matter breakdown? So here, hydrolysis there, acidogenesis, acetogenesis, methanogenesis. So I hope that you guys know all this different phenomena which you may have referred from the lectures. So here, then we see that uh, in this process, why we are telling that methane is produced. So people are using this methane for, this is a renewable energy that we are getting. So we are not using fossil fuel. We are we are not using any other plants, wood and all for. But here we are getting some, this gas which is methane, and this has the potential for the energy applications. So this has the potential for the energy. Oh, sorry. So here, this methane which is produced from this process has a great potential in the energy application. But here also you see the production of carbon dioxide also there. But when we compare to the fossil fuels burning and all, this amount we can actually neglect. So now you see that what is the methanogenesis? During methanogenesis, methanogenic archaea convert acetic acid and hydrogen into methane and carbon dioxide. So this is the major process you see. This is the equation. So you can refer the slides once I upload. And here you see the biogas composition. What is the biogas that we get? The final biogas produced during anaerobic digestion primarily consists of methane. That is around 50 to 70 percentage, and typically also 30 to 50 percentage carbon dioxide is also there. Also, some other gases which is hydrogen sulfate and other trace gases. So, this energy, this methane is very high energy, and which I explained to you, it can be used as a renewable energy source. Okay, and also you see that, and we can also used for the electricity generation, heating, or as a fuel. So this particular process has a great potential for the renewable energy application level. Okay, and carbon dioxide, you know that when there is a natural degradation or by happens this byproduct, uh, carbon sorry. Yeah. Now this biogas which is used directly taking and using in the home supplies and all that, right? Yeah, so the storing and all, I hope that you can store it. But normally, if you start from a homemade, like there are different, I think agencies are there, so they'll come to your home and build this setup, and you can actually, use. But this is not that much widely have started. But I have seen some projects they have started, and even that we can directly take and fix it into the stove and use. But oh, yes, yes, that is there. But when it is a small, saying like small scales, small things, like for um, that depends on what we give also, right? What we are giving, like the amount of the waste that we are supplying. Right. So for the homely, I'm saying the for small scale, that is possible, I guess. But when we go for the majorly, when we go for the large scale industries, yeah, that is different case. Yes. So now even I think in our government also we are promoting more of the renewable type of energy because of want to eliminate the fossil fuel. So you have heard about this ethanol mixing in the fuel. Have you heard that we are reducing we have to develop engines for ethanol for the vehicles, but now what we are facing is the corrosion of the engine parts. Yes. So okay, that is bit different, but yeah, renewable energy sources we were getting, and electricity is also like so important thing that electricity we get from the microbial fuel. You know that microbial fuel cells, right? Have you heard of that? Yes. Okay, in microbial fuel cell, even in our lab also we have the small like microbial fuel cell, but that is very small cylinders which we can even take with hands, very small. So in that also we can wastewater is there, and we supply this the microbes, and what happens that it start because of the reaction we can produce the electricity, but I can't explain that how exactly the electricity is produced from that. But that electricity that what we are getting is around very minute, okay, below 1 volt, but that we have to improve by supplying different modification. Okay, that are those things I will take in the last class, like that interesting informations. Okay, then now we have discussed that three types of anaerobic reactors: upflow anaerobic filter reactor, anaerobic baffled reactor. So now we starting with upflow anaerobic sludge blanket reactor. So here you see wastewater is there. Here we are providing from the, see here, it is from the downward to the upward, the whole system works. So I will explain you. So here majorly, okay, so majorly, these are the different, components. Upflow of the waste. So see, wastewater enters the USAB reactor from the bottom and flows upward to the through a bed of granular sludge. This sludge is known as sludge bank blanket. So here you see wastewater enters from here down, and then it is going upward, and you see here the sludge granules are here, and you see the microorganisms are in that, okay, and contains microorganisms. Okay, that is the one which break down the organic matter um, uh, in the waste. So here then anaerobic digestion happens as the water pass through the sludge blanket. Organic matter is decomposed by anaerobic bacteria, and this process generate biogas. You know what is biogas, in which the primarily is methane and carbon dioxide. Then the biogas rises to the top of the reactor and collected in a gas collection system. Okay, then here also sludge settling is also here. The treated wastewater now with reduced organic content exits the reactor from top. So some of the sludge may also leave the reactor. So additional mechanisms. Okay, recycling. Here I haven't shown the recycling. We can also connect with the recycling tank. Also here you can see this outlet, and also we can again supply back through the inlet for the recycling, for to increase, to maximize the maximum usage of the granules and the wastewater. And you guys have heard about the zero liquid discharge. So if you want that zero liquid discharge, if you want to attain, then you have to think about the recycling also. Okay, so then you have to think about the recycling also. So here, the mainly the treated effluent is discharged from the top of the reactor. Okay. So also you see that as I explained, we have discussed on the previous aerobic also. primary, secondary, and tertiary. In tertiary treatment, you need some disinfect the water also if you want to use it for, for different. If you want to just supply for the plants, for the growth of the plants, you can just directly supply if there is no harmful elements are present, if even for the plants. Otherwise, if you want for the human usage, again you need more treatment. Okay, so now you see here, upflow means from the up down bottom it will enter, and the microbes are there in here, and it will treat, and we are biogas is generated from this position, this region, and it is collected, and then the outlet, the is here, the effluent is collected. Also, we will think this effluent need to be treated again if you want to use it for the different things, or if you want to discard also, think about the WHO, there is some limited amount of component chemical composition is there. If it's under it, it's fine, otherwise we need to treat it. So now, so here I have given the different components, also the functioning also, so you can read this. So next is the, okay, so now next is the anaerobic filter reactor. You see here there is a filter reactor. Filter is also here. So how this is different? So when we see here in the upflow, you see this, it is coming from here, and it is all the process happening here and going here. So now here you see it is coming from the top. So this is the inlet. Then it is it's like its movement is from here, and then there is a bed of filters are here. Then it is going upward, and this filter has microorganisms. Okay, so this filter has microorganism which will um, degrade the organic matter in the wastewater, and the whole process is happening in this way. So this here you see the main components are reactor vessel is there. It is the main chamber where the my wastewater is treated, and then filter media. Filter media is this portion. This is the filter media. Okay, this is the filter media, and here the filter media, the packing material inside the reactor, that provides surface area for the growth of microorganism, and it can be made of various materials like plastic, ceramics, or other inert substances. So this media is should be arranged such that it should have a good contact with the wastewater that we are providing, because there only the microorganisms have to process the waste in the water, right? So here you see that it is very densely packed, but we have to make sure that this packing media, which may be a ceramic or the plastic in which we are providing the microorganisms, and this is the wastewater that we are providing, and then the wastewater that we have the organic matter. So this should have good contact with the microorganism which is in the plastic or ceramic or any other filter media that you are providing. So then only it can efficiently react with the, get the time to eat the matter, like it is like it get processing time, and it has a good contact with the wastewater. Okay, so that the packing also we have to uh, take care of. A good packing is needed for the perfect working of this reactor. Then you see that inlet and outlet pipes, that for the entering and going out, and gas collection here, a system to capture and remove the biogas produced during the anaerobic digestion process. And this typically include a gas collection chamber and piping. Okay, so the piping is provided to take out the gas which is produced in the system. So also we need to remove the sludge. So the sludges also we have to remove. So mechanism for periodically removing accumulated sludge and solid waste that settling in the reactor is also needed. This can be manual or automated system. Yes. Yes. Huh. Yeah, piping means like you have to see piping means we it see here it is you see that here the biogas is produced here. So then you have to uh, you know which is produced there, you can connect what pipe here, and then you can collect it and you can fill in the another chamber. Not getting. So here you see anyway this so here the biogas it is producing, so it will fill in this chamber, so you have to suck this out, so you have to take this out, so anyway it will flow and it will take, it will move. But then you need a chamber also, you have piping means it's a mechanical compartments that you need to take it out and store it, like that. Okay, got it. Okay. So then sludge removal system, you know that if the sludge after a while, the sludge will settle and we can manually open the system and then it can remove, or you need some other parts. So you can anyway, so if you have a basic system, so when you started working with a system, whatever modification you wanted to do, you can just do automatically you can see the operation. Okay, you need you can make a design, or just you can manually how you can flow this out, because you can make an opening somewhere, and you can actually when it start working with the reactor you can do that modification without affecting its basic principle. Okay, so now mixing system in some design. So here I haven't shown in some design mixing system can be included to enhance the contact between the wastewater and organ. This can be achieved to mechanical mixer. So like that. So here we feel that it is densely packed. So when we give some turbulence, we give some force. You think of a fan. You think the fan which is here. If we operate a fan here, what it do? So it will rotate. When it rotate, you can imagine that this water surrounding the fan will move. So that will what happens? It will give a pressure for the water, so that when it fan moves, the water also pushes. It will move little bit more speed and it will hit the the media which has the microorganism, so it will get in touch more. If there is some gaps, if it's a closed region is there, the microorganisms are in some of the region where the normal flow it can't penetrate there. But when we provide a the flow here, if you fix a fan, I'm saying here, the mixer here, it will actually force the water to move through the media, and it will get the organisms get it get more supply, so that we can improve the efficiency. Also that time you have to think of the energy consumption also, so you have to think about energy consumption, and also you see that how can you minimize that, and you can supply the mixer here to improve your efficiency. Then temperature control system in certain application maintaining specific temperature. So, as we have discussed in the previous week, that different organisms require different specific temperature. For that, if you want to keep the temperature, you can provide those temperature control systems also there. So, insulation, have you heard of insulation? Also, we can you can properly cover the system. For heat loss, you can minimize from that. So this is the functioning. So you see, you can read this whole. Now, the third variety is anaerobic baffled reactor. So here you see baffles are connected. What do you think that what it does? Because we already discussed about this baffles in our discussion. What you can guess what it actually does? Can you think of what it is? What actually this baffle can have elevate? Yes. Then how this is actually, see here in all our previously discussed two systems, it is coming and it is entering, and the whole operation is over within this time, right? Here, see, coming and going. So what this baffles, yes, yes, right. So it is getting more path. So here, if you just take off, just imagine that you are taking off all the baffles from this. Okay. So then what is happening? So it is coming and going this way. So see that it is just going in the wind. I'm not saying that going through it quickly. I'm just telling that the movement is only from here to here. So if the baffles are not there, so now what it has to travel from all this, all this way. So that it is increasing the time, so it is giving more time to. Okay, so now what is happening? It is increasing the time for the processing. So we are getting the microorganisms are getting more time. Look, it can process it. It will be very happy that it can, you know, uh, it can process it. They are getting more time. So here you see it is a reactor vessel is there, the main tank where the wastewater is treated. And now you see the baffles. So here the internal partition, that is the baffles. Internal partitions are the baffles. And then inlet and outlet pipes, that and biogas collection system, and then sludge removal system. And the main working principle here, you see wastewater enters the reactor and is directed through a series of compartments, and it these compartments are mainly formed due to the presence of baffles. Okay, so each compartment allows for different stages of the anaerobic digestion process. And mainly here you see the retention time. So the design of this baffles ensure that the wastewater remains in the reactor long enough for the microorganisms to break down the organic pollutants effectively. So they are getting more time. Okay. And here, biogas production during the anaerobic digestion process, the microorganism decompose organic matter and then produce, as we discussed for the previous chambers. Then, effluent after passing through the various compartment and undergoing treatment, the treated wastewater exits the reactor to the outlet pipe. And also, even if it's treated through all this compartment, we need the tertiary one disinfect the water if you want to consume. Okay, so you understood different type of anaerobic reactor setups. So this is the baffled one, and then we discuss about the anaerobic filter reactor, and this is the upflow anaerobic sludge blanket. Now we go for the questions. Okay, then before that I have just given a table for difference between the three reactor. So you can just see, understand, I'm just telling about few things. So here the we understood in the design, anaerobic means packed belt or filter media. Here anaerobic baffled reactor, you see the baffles are there, and upflow, here a single vessel. So you can read this and understand the difference. So now we go for the question. The advantage of anaerobic wastewater treatment over aerobic process. So four options are given: higher organic loading rate, lesser biomass synthesis, lesser nutrient requirement, D, all of the above. What will be the answer? Anyone can tell? Anyone can answer? Advantage of anaerobic wastewater treatment over aerobic process. Okay, the answer is D. Higher organic loading rate, lesser biomass synthesis, and lesser nutrient requirement. So you know that lesser nutrient requirement means it doesn't need that much nutrient also for the uh, for the waste microbes to react. Okay. Then second question, the biogas produced during an anaerobic wastewater treatment is primarily composed of. So that we have discussed in what will be the answer? A. Yes. Methane and CO2. Okay. Now, methane is produced during methanogenesis form. A. Acetate. B. H2 and CO2. C. Both A and B. D. None of the above. Methane is produced during methanogenesis is from which one? That is also we have. A. Yes. Right. Acetate. So this you can read. Now, fourth, generally, the rate limiting step of anaerobic treatment processes methanogenesis, acidogenesis. Yes, yes, right, hydrolysis. Next, an example of a conventional anaerobic reactor is A sludge digester, B septic tank, C open ponds. What will be the conventional anaerobic reactor? Yes, septic tank is right. But you can also say this also sludge digester is also anaerobic reactor. Okay, this both will come. So the answer is this one, both A and B, sludge digester and septic tank. Next, the correct sequence of a UASB reactor from the bottom. So what will be the from the bottom? Okay, you understand that the correct sequence of UASB reactor from the bottom. So that you already have seen. You have seen this picture, right? Okay. Now just just tell me this. So the correct sequence of UASB reactor from the bottom. B is not the answer because you go GLS is for the class X yeah, class yes. Where is the okay okay. So the question was this is the upflow anaerobic sludge blanket reactor. So from the bottom, start the components from the bottom. So what is the first one? Inlet, right? This inlet is the first one. Okay. Okay, I can't. So you have seen that picture, right? Now you see answer is this one D. So because this is the inlet flush, first one is inlet. C B what you have told is settling. So this settling is not the bottom because here in USAB also it's upflow. So that only we have discussed. So upflow only it is happening. So upflow means it is actually coming from the bottom, then it is releasing from the upward. So that's why this is like inlet, then slash blanket zone, then settling zone, then GLSS, which is gas, liquid, then what solid, right? S stands for the separator. Yes. So that means okay, we'll go for again there. Any confusion is there on that? See, this is coming from here. Inlet is this portion. Then only it is settling. Then, okay, we can't see. Then the last one is the collection one, which is the here, this portion. It is the gas GLSS. Yes. Sep system. Yes. Okay. Got it, right? Okay, so this graph don't confuse because I just selected the basic graph. So in this you can't actually see in that. This is the settling is here. It happens here settling. Then we can manually remove the settlings, which is settled. Okay. Uh, because I yes. Okay. Sludge blanket zone. Yeah, sludge blanket zone. See, sludge blanket, what is from there also you get that. Sludge blanket means it is sludging is making a blanket. Okay. So that we have to from there the settling is coming and that is we are removing from the upward portion. Got it? Okay. You see here, anyway, when because of the velocity it will come down and it will be because of gravity it will be here it may settle and then what happens is it become a blanket where it become blanket and then after that it settle on it. What we removing is we were removing from the upward portion after forming a blanket. After that whatever it is falling on that portion, then we are removing on the upward region. That's what. But I will show, if I can, I will show in the last the class that some good picture which depicts each zone. Okay, I will show this class only in the last portion that I will show differentiating the regions. So this is just a basic diagram. Just don't confuse it. I will show you after all the questions are done. I will show that some other graph. Okay. So now, seven question in a UASB reactor, the sludge blanket zone is majorly responsible for. So, A, degradation of organic matter, B, solid settling, C, gas collection, D, all of the above. What will be? No, here it is mainly the degradation. A. A is the answer. Degradation of organic matter. There it is like okay, see, when the it form a blanket, so there will be a lot of organisms are there, right? So when the inflow from the water comes from wastewater comes from the bottom, it will hit in the blanket, and then the organism which is in the blanket, it will start, processing the organic matter, and then all the from the all our boundary of the system this process happens, then the sludges which is upward also making a sludge. When the sludge become bigger and bigger it will come down. Even the blanket serve as a media for the whole operation, but after a while, the after the processing these microorganisms will be there, even the sludge which is above the blanket also. Then these organisms after the reaction the sludge, when if it's become the flocculent types, they also if the mass of the sludges become higher, then because of gravity it will come down, but also we are providing the inflow, so for that the force is going up. Got it? Is it confusing? Okay. Okay. I will show some other picture for the explanation of this one. Okay. Yeah. Degradation of organic matter is the answer. I will show a graph which separate this. That will be clear, I guess. So now, eighth question: biomass separation in an anaerobic contact process can be improved by biomass separation in a anaerobic contact process can be improved by four options are given using parallel. This, see, we are not telling about the biogas production, we are telling about the biomass separation. Huh? A is the answer. Using parallel plate separators. Parallelly, see, if we have a parallel separators, we can easily separate the biomass. That's what this is about. Okay. Sorry. Sorry. Okay. So someone else also talking. What you are telling? Please tell me. Then I will answer for both. Yeah, yeah. Yes, yes. I got it. Sangamita, I got it. I think one more person is telling something. Sorry. Only you know. Okay. 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 Fine. Fine. Okay. So here. Okay, in this diagram also, see, we are always we want to separate this biomass, but we can't see when we have the parallel separator. See, if you have some parallel separators here, when the sludges are settling down, we can actually take it out. If we have, it will come down and parallelly. Then what happened? We can just take like that. We don't need to uh, in this system we don't need to only concentrate on one portion. If it's have different settlers here, then what happens, we can easily separate from those things which is fixed in the parallel. Got it? Okay. Okay, then I will, that also I will show some diagram. That is bit okay. Okay, then next one. Okay, now we'll take a break. Then after 5 minutes, we'll start. Also, we have problems also, like, so keep calculated. Fine. Yes. Okay, we'll start. Okay, I have downloaded one image for you. I just download it. Okay, I will download it and I will start. Okay. Is the screen visible? So here you can see um, this is the wastewater which is flowing from the down. Then it is all the process normally what we are seeing in the other systems are going in horizontally or in coming down or something like that, or mostly like in in the same level. But here you see that wastewater is coming from the bottom and this is going up. So you here see this is the uh, pipe which is going inside, and this is the influent that is distributor. And here you can see here this is the sludge granules containing bacteria that sediments to the bottom. So here you see this granules here. It has the microorganism, and as I explained to you that when the wastewater move from this direction and it is actually going in this passion, so it is there is a force, the movement of water happens to the upward direction, which make a turbulence motion. And due to that turbulence, that is that beyond biogas bubbles, they okay, that is the biogas which is produced. And also you see that sludges also, after this turbulent flow, it is actually transporting in the different regions. After certain point, these sludges also will come down from different direction. When this, the weight of the sludge become higher, and it will become the that weight will overcome the velocity of the water here, so it doesn't have the power to lift again the sludges back to the uh, surface. So like that it will turbulent and again it will come down and settle. So, okay. So, next class I will find some other graph. Then I can explain you more clearly. At least this graph compared to the previous one, it is more clear, I hope. Yes. Okay. Now, this one we have taken this eighth, right? We have reached eighth, right? So, till what question we have reached? Anyone know? This eight, right? Eight or 10? Eight only, right? Okay. Huh, yes. This one. This is not done. So next, this question: anaerobic processes are perceived not suitable for options: wastewater with lower concentration of biodegradable COD, operational lower temperature, nutrient removal requirements. D, all of the above. So we anaerobic processes are not perceived because not suitable for which of the options given below. Yes, right. All of the above. wastewater with lower concentration of biodegradable COD, operational lower temperature, and nutrient removal requirements. In these things, anaerobic processes are not perceived or not suitable. 10th, anaerobic fluidized bed reactors are operated as upflow reactor. B, require low density media like plastic beds for attached growth. C, require energy for fluidization. D, all of the above. So what is the anaerobic fluidized bed reactors for? So anaerobic fluidized bed reactors for all the which is, sorry. So no, it is actually for all of the above. D, yes. It is or operated for upflow reactor and require low density media like plastic beds for attached growth. So why this low density? If it's high density, yeah, yes, yes. Then require energy for fluidization. So this answer is D, all of the above. Now, the percentage of methane in biogas produced, 11 is done, right? Okay, which of the 11 is done, right? Not done. Same. Okay. Which of the following anaerobic treatment system required inert media for operation? So, A, anaerobic filter, fluidized. Sorry, just think more. Yes, all of the above. Yes, all of the above. So, an anaerobic filter, fluidized bed reactor, anaerobic fixed film reactor, all of them need inert media operation. Okay. Now, third question, 12th question, the percentage of methane in biogas produced from an anaerobic wastewater treatment unit. So, whether the percentage of methane it is produced, whether it is decrease with increase in COD by TOC ratio of wastewater, B, increases with increase in COD by TOC ratio of wastewater, and C, independent of COD by TOC ratio. D, all of the above. What do you think? Percentage of COD by TOC. Which what do you think that answer correct answer? Percentage of methane in biomass produced. Anyone can have answer? No. Sorry. No. D is also wrong. This one, B, yes. Increase with increasing COD by um, TOC ratio of wastewater. So, what is TOC? Yes. COD. What is COD? Yes, chemical oxygen demand, right? So, here, what is happening here? The percentage of methane in biogas, we need more percentage. So if you need more percentage, then what you have to do is you have to here what this means, that increase with increasing this means COD by TOC ratio is higher, means what meaning that we are reducing the TOC, right, total organic content. Total organic carbon we are reducing. Yes, sorry, yeah. Total organic carbon we are reducing. So that means that we need this one, total organic carbon we need less, and the chemical oxygen demand that we need higher. Okay, so this one, okay, I will tell you with some elaborations. Just wait for after this class get over. I will just tell you, like, with some things that I will to show you. So I will go for the problems now. Otherwise, the problems it won't end. We have only two problems, but one thing is that have you guys referred this that question that I have shown you, this one that we have taken in the previous class, and then there was some confusion came in the unit that we have arrived, huh? Have you tried this question? No. Okay. No. Okay, then let us start with this question, because otherwise, okay. So first of all, see, an activated treatment system to be, this is all about thing. This is not an anaerobic system. This is need oxygen. Okay. So see, we need oxygen for this. This system, an activated treatment system, is to be designed for treating 18,300 meter cube per day of municipal wastewater with a mean cell resident time of 10 days. And soluble BOD in the influent is 150 milligram per liter, and the desired soluble BOD in the effluent is 5 milligram per liter. Assume MLSS concentration. What is MLSS? Yes, concentration of 3000 milligram per liter and overflow concentration of 10,000 milligram per liter from the secondary clarifier. Consider the following values for kinetic parameters obtained from Pirate scale analysis: y equal to 0.55 kg per kg, kd zero point zero 0.04 per day, and a tank volume of 6,100 meter cube. What is the volumetric loading rate? So what we have to calculate, we have to calculate three things. So first one, volumetric loading rate we need to calculate, and then that is the first one. And then second is we have to calculate total biomass production, and three is average biomass concentration. Okay, these three things we have to calculate. Okay, now I hope that you guys also have the note, and you can start. I mean, you can just scribble down the data which is given, and we'll start. So first aim is we have to calculate the volumetric loading rate, right? So first of all, we have a system. We have a system, and we know that the system, the chamber has the volume of 6,100 meter cube, and then inflow is there. What is the inflow rate? It is system to be designed for okay, inflow rate is not given, and then this is the influent, and then the influent BOD, sorry, where is the influent BOD, is this one, 150 milligram per liter. Okay, then effluent, which is 5 milligram per liter. Okay, so we have noted down this one, and then this one, and we have two constants here. Yield, what is y means yield coefficient, so here I will write, okay, y is equal to 0.55 kg per kg, and then kd equal to 0.04 per day. And then what else? It is now we know that this is also given. The treatment system is designed for treating this 18,300 meter cube per day. So here this is the system. This system treats 18,300 meter cube per day of wastewater it is treating. Okay. And then residence time 10 days. Then assume MLSS concentration. So what is the MLSS concentration? Okay, this we now we are not okay. MLSS concentration is 3,000 milligram per liter. Yes. Okay. This this refer in the previous one because this doesn't have much confusion. Only this from here only it is starting. MLSS is equal to 3,000 milligram per liter, and what else is given? Nothing. Yeah. Overflow concentration is also given. Okay. So overflow 10,000. Okay. 10,000 milligram per liter. Okay. All these are not needed for the second and third. So these are we had stuck in this one, this particular thing. So we have to calculate the total biomass production. Okay. Now, or else this you have any confusion? This one, what oleometric loading rate? Yes, yes. Point 0.5, 0.45 kg per meter cube day, right? This is the answer. Okay, now we go for the this doesn't have confusion. This is easy, I think. Here. Now calculate total biomass production. The question was this one. Sorry, sorry. Formula for the this one, right? Okay, volumetric loading rate. This is the mass of volume of the yeah, right. Okay, thank you. So divided by tank is 6100. Yes, this is Q here. SI this one. Okay, this is fine. Now calculate total biomass production. So here we start. What is the can we can we start in the next page or okay? This these things you have noted down, right? Okay, I'm starting in the new page. Okay, so now what we have to do is total biomass production. So here, okay, total biomass production. Let's say that we'll write XT total biomass production. So that is equal to L naught or into Y yield divided by then S in minus S out. So this is the formula for the total biomass production. Then I will write what this means. So this xt is the total biomass production, and l naught is the influent bod load. Okay, influent bod load. This is in kg per day. Okay, then y is the yield coefficient, which is already given. It is like kg biomass biomass per kg bod removed. And then si is the influent bod concentration. Influent bod, which is in what mg per liter. S out will write, that is effluent. That is also in mg per liter. Now, uh, now what you have to do is see what here SI, which is what influent BOD, which is given here 150 milligram per liter. So here 150 milligram per liter. So convert it into kg per meter cube. How do you convert? Yes, 10 to the power minus, that is 1 kg per meter cube. So like that, you can also write S out effluent is equal to, see here this is, yes, 0.5. So now X is equal to, and L naught also we have calculated in the previously, it is coming around 2745 kg per day. Okay. So now we have X is equal to 2745 into yield. What is the yield here? It's 0.55 uh, divided by this one, SI 0.15 minus 0.005. So what is the answer here? So 412. 412, right? So here the main thing comes here 2745. This is kg per day. Okay. See here the unit also kg per day, and then here this is kg per kg divided by here kg per meter cube. So in the previous class, the doubt was here that when we actually cancel out the things here, the kg things, the remaining was what we thought this god was meter cube per day, right? Remember, the thing is here what we are doing, like considering here, we are not considering in meter cube per day, because in sludge it is most of the sludge mean here it is a solid thing, so we are considering it's like a weight. So we are not considering this normal conversion here. We are just considering this like the for this particular x, the final we are just taking less kg per meter cube. Sorry, kg per. Sorry, just wait. Yeah, kg per day. Okay, we are not considering meter cube per day. So the thing is here, meter cube means normally it is most of the things we have to consider in a liquid form. But here, what we are dealing is with this, you know, what this sludge here, it's the solids also here. We are considering this like in a weight form, not in a meter cube, because this is not a pure liquid that we are considering. So that's why here we are directly taking like the value is like kg per day. Got it? Yeah. Yes. Sorry. Yes. Yeah. Yeah. Yeah, you have to write like this, because this particular for the total mass production, you have to, you have to take like kg per day. Yeah. As far as I have done multiple times, but I am like, when we do the actual this thing, when we cut out this, is like meter cube per day is coming. But in all the like referring, when I referring the, the booklets, it is like mentioning like it is like kg per day. But if I don't know, like in some inbuilt meaning is like what I have got to know, like this thing is like this is a solid is coming, the what the liquid is not fully pure, and so that we can't mention like it is meter cube per day. Normally we are taking kg per day. That's what. So anyone have any comment on this? Anyone? Okay. Sangamitra, okay, I will even even whenever throughout this mass things, like when we do that, we have to consider that. But even here, even the booklet, and I have seen in some textbook also this thing. I will again check if you have the doubt. Anyone this particular problem in other class also people have done? Can you hear me? Okay. Okay, then consider like this. So you have gone through this the same type of problems in other classes also this type. Okay, okay, fine. Let me also again. Okay, but as far as I have understood about this problem, like since it's a sludge, we have to take like kg per day, not meter cube per day. But still I will, okay, I can talk to some like some other professor or some like for the this particular, the activated sludge process, and I will let you know in the next class if some correction is there. As far as I understood, this is the final thing. Yeah. So then, okay, this is the X total biomass production, that is we got kg per day. Then how you have to consider that now you have to go how to calculate the average mass flow concentration. So that one is the same thing that we have done, only this unit thing that I am clearing here, so you can go and refer that. Okay, so only this thing, this unit is the main thing I have to discuss here. I will go for the other two questions. Other way, I can't end this question. So if you have, you do this, and let me know if any doubt is there. I will clear this out. This thing, this particular question. Yes. Yes. Kg per meter cube day. 1 point. 1.72 kg per meter cube, I told. No, not kg per meter cube. That answer is not with me. Okay. I'm sure that it is not kg per meter cube. I thought I would have told 7.2. Uh, I hope that I have explained that 7.2 milligram per liter. I hope. Okay. Huh. Days coming. Okay. Okay, I don't have that answer now with me, so I will just like compare those things and finalize this one next week. But this about this till here, what I told about total biomass production, this is the kg per day is the unit. Kg per day is the unit. That is the till now. This is the finalized, and I will cross check with this answer for the previous lecture answer, and I will do it in the next week quickly. Otherwise, okay, is that fine? Yeah. Okay, now we'll go for this week problem. Okay, this is the problem. In the process of methanogenesis, acetic acid gets converted into methane and carbon dioxide as per the reaction. Okay, then considering 80 percentage conversion efficiency, the methane gas produced in meter cube in a reactor fed with 10 mld wastewater having 180 milligram per liter acetic acid would be approximately. So now what we have to find from here is we have to find um, what we have to find from this equation. We have to find the methane gas production, how much methane is produced. So they have given the details of the reaction. So now what we have to do is, so for this first step is we have to find the total mass of acetic acid per day. Okay. Total mass of, I'm just writing, total mass, total mass of acetic acid per day. So this we have to find out. Now how to find out this? What we got first from the question. So in the question, it is given, this particular thing is given here, flow rate, flow rate of wastewater. What is the flow rate? It is 10 million liter per day. So that means how much comes? 1, 2, 3, 3. That is liter per day. Okay, so that this is the flow rate of wastewater flow in the whole system. And now the concentration of acetic acid, right? Yes. What is the concentration of acetic acid here? 180 milligram per liter. Now the total mass of acetic acid. Acetic acid in the wastewater matrix. Acid in the system equal to this. You have to multiply the flow rate of wastewater liter per day into 180 milligram per liter. Yes, this also liter. The answer comes 1.8 into 10 to the power 9 milligram per day. Okay. Then you can just write in kilogram, milligram. How do you convert? Then gram. It will be like how much milligram? You can convert into kg per day. So now that will come 1.8 into 3. That will comes like 1800, right? 1800, right? Kg per day. That is the first step. So we know the flow rate of wastewater, that is 10,000 10 into 10 to the power 7 liter per day. Then concentration of acetic acid 180 milligram per liter, and total mass of acetic acid in the system. You have the concentration of a specific acetic acid, and then you know the flow rate of wastewater. So you can just multiply, and you got the total mass of acetic acid in the system. That is the first step. Then you know the next step, you know the conversion efficiency. So the next step, I'm writing it here. So you know the conversion efficiency. What is the conversion efficiency here? It is 80 percentage conversion efficiency. So here conversion efficiency is 80 percentage. So now, so when you have this efficiency also, you know that the conversion is not 100 percentage. So now you can just consider this also. Then you can just write the mass of acetic acid converted equal to 1800 kg per day into zero point 0.8, which is equal to 1440. Yes, right. 0 kg per day. Hope till here it is clear. Now we go for the next step. Now the third thing is, okay, now the third object step is, we have to find out the moles of acetic acid converted. Moles of acetic acid converted. So now we have the molecular formula CH3 C double OH, and now the weight is 60 gram per mole. Okay. Now the moles of CH3 C double OH, moles of acetic acid. Now you have the total converted here. What you have, it is 1440 kg, right? Kg per day we took. It is any one day, it is given in the process of methanogenesis convert into it approximately. Okay. Now we have 1440 kg per day we have. Then here it is 60 gram per mole. So now you convert any one of this kg or gram, then find out what is the moles of CH3 C double OH, so acetic acid per mole per day. Found 24 into. Yes. Yes, 10 to the power minus 3. Yes. Everyone got this answer? Yes. Okay. So now fourth thing is social. Sorry. Huh. Okay, I have 10 power 3. So you see this gram also there? Okay, let me also calculate. 1400 divided by 6 into. Yeah, so this 1 gram, if it's converted into kg, so something, yes, the minus won't come, I guess. See, this become, yes, because see, this 60 means here you see that 60 gram. So you're converting into kg, it become like point zero 0.06, right? So this is like 0.06 because 60 divided by 1000 you're doing. 60 by 1000.06. So then 1 4, because that is the lowest, your denominator is very low, right? So then it will be like high. Okay, 1440 divided by 0.06. It is like 24,000. That is the answer. Yes. Sorry. So now it is like plus it. Okay. I'm just writing 24, 1, 2, 3. This is the answer. Okay. Now, sociometric metric of the reaction. So when we see first, we see the equation CH3 um, COOH equal to methane plus CO2. So this is the equation. Now we see that this particular equation, when we consider, this indicate 1 mole of acetic acid. When we consider this 1 mole of acetic acid produce 1 mole of methane, right? From this equation, 1 mole of acetic acid produce 1 mole of CH4, which is methane. So now from this particular thing, we can convert the moles of methane to mass. So here we see also, okay, sorry. So from here, you know this thing. Now, understanding this particular statement, so we this means that 1 mole of acetic acid produce 1 mole of methane. That means what? So here we have calculated moles of acetic acid. That we got this 24,000 mole per day. So this means that moles of CH4 production is equal to what? Can you say? So we know that here 1 mole of acetic acid produce 1 mole of methane. And we know that in this whole system, the moles of acetic acid that's converted here, we got the answer. So then correlating this thing, can we directly say the moles of methane? Yes. Yes, right. 24,000 mole per day. Got it? Any doubt in this statement? Like this thing? Any doubt? Anyone? Okay. So from here, you have to convert the moles of methane into mass. Now that we can do. Till here you got it, right? Now what we have done is we have calculated the total mass of acetic acid, and from the balance equation we know the amount of acetic acid. 1 mole of acetic acid means 1 mole of methane, so we can correlating the amount of acetic acid produced and then, sorry, converted, and then that particular value, this we got, is correlating with the amount of methane which is produced. Now we need to convert this particular value into mass. Okay, now next step is we need to convert moles of methane to mass. So just tell me, what is the molecular weight of methane? Yes, 16 gram per mole, right? Now mass of methane equal to 24,000 mole per day into 16 gram per mole. So the answer, what is the answer? Multiply 10. Okay, 384,000 gram, right? Converting into kg, 384 kg, right? Got it? Then next is how to calculate the volume of methane. Volume of methane. So for the volume of methane, we should know the density of methane that is given in the question. See, the assume the density of methane is 465 kg per meter cube. Okay. Now density of methane equal to 465 kg per meter cube. So the volume equal to, how do you calculate volume? So we know the total mass here. So you know the right, density is equal to mass by volume, right? We have the density here. We have the mass here. We should know the volume. So volume is equal to mass by density, right? So mass is 384 kg divided by density 465 kg per meter cube. So now, yes, 0.826 meter cube. One more thing is, yes, here you here see here we are cancelling out, and here it's come day also coming. So normally here also we are like, if you consider 1 day operation, So we are not considering per day, so here it comes like per day. So here also, if this per day is there, day. So in final answer, if it's come like meter cube per day volume, but we should consider like a volume means in, we have to take it like in meter cube. So in one day operation only, here it is, just assume that it is on day operation. So on day operation, then from here we don't need to consider this day. So we can just directly write like oleum is 0.826 meter cube. That's what it is happening. So it is like per day operation. So the whole process is, we are assuming like an one day operation. So like that, when you consider like this particular thing, we don't need this thing. We can just directly like 384 kg. You can write like mass of this methane produced in one day. Like that, we are finally reaching here 0.826 meter cube. Got it? Any doubt in this question? No doubt, right? So I think I will stop here, because if I start also next question, I can't complete. In next class, I will cover this question and this one. So this particular question is like, if anyone also like can comment on this question, please. I'm like, you can comment also this particular question. Um, okay, so then any other doubt in the today's class about the theory that I have taken, this one, this thing about this three type of reactor? Any doubt? Yes, yes, I am uploading the slides in the drive. You can access my slides. Yes, I'm sharing. So you may have shared a Excel file, Excel, right? So in that, from the three lectures, like three people are taking, for the people, three link for the lecture and link for the drive is also there, right? So in that, in my name, I have given a link for the drive. So in that, you get it. Okay. So any other doubt? So if you want, yeah, if you want, like I will take about that parallel one. I'm not getting the exact picture for the parallel separator of biomass. So in that I will cover slightly. I will cover this upflow, this one. Yeah. Okay. Design in the sense the graphical, like how the proper, you want different compartments like that, or design. Yeah. Okay, so you want the graph in the sense pictures, right? Pictures, pictures or design. Okay, design. Yes, yeah, that I will. Formula. Yeah. Okay, okay, okay. Assignment seven. Okay, in your assignment sheet that it is provided, right? That one, huh? Okay, okay. USAB. Okay. Design, USAB design, right? The question, can you just yeah, can you huh? Okay, okay. Then I will take it in the next class. Yeah, surely I will take. So can you just type this? Okay, can you just send me the question? You know my email ID. Okay, I will just that question you can share. I will type my email ID here. Where I okay, I will just okay, I will just write my email ID here. Just yeah. Now, if I share also, like I can't snapshot it. If you send me, then it will be good for me to roughly like. Otherwise, I have to see this video. That's why. Is it fine? At 93 at gmail.com. Yes, yes. AISWARYACL. Yeah. Otherwise, this also you can say if you are confusing, 0026 at tv.ac.in. Yes. In this, any of this, please share the that question and next class I will take it. Yeah. No, I am not taking tomorrow's lecture. I think there are other two TAs. They will take next. Yeah. Till this Wednesday. Okay, okay. She is taking that. Okay, okay. No, I don't know that what they will take, but uh, six to yeah, yeah. So the you people can join that class. Yeah, yeah. Design. Yes, yes. So I can take on next Monday because my turn will come on next Monday. Yes. So you people join on. Huh, sorry. Over. So tomorrow there is one class is there. Na Sangamitra, what is the timing of that class? Six. Akash. Oh, yeah, yeah. Akash. So okay. Yes. So yeah, yeah, sure, sure. So next Monday I will discuss. So tomorrow, please join on that class, 6 to 8, right? Akash, right? Yes, yes, Akash. Yeah. Yes, yes, yes. So join that. Yeah, I think. Anyway, I will take next Monday. You people can join that class and get to know about that. Yes. So anyway, you share that question, and next week I will take. Okay. 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 Fine. Anything else? Okay. Thank you. Okay. Thank you. Thank you very much. Thank you.